Okay, so we're going to talk about rational functions in this section. So a rational function is just a kind of a fraction of polynomials. Rational numbers are fractions. Rational expressions are kind of like rational functions in that anytime you see that word rational, we're talking about like a ratio. So we have one unit on top of another unit. In this case, we're talking about polynomials. So a rational function just has the form p of x over q of x, where p and q are both polynomials. And typically we're going to assume that p and q are not going to have any factors in common. We will see some, at least one in the notes and maybe a few in the homework, where you do need to be able to factor them and cancel some things out. And then we'll see that maybe they're not actually a rational function after all. So we'll take care of those when we get there. So just as an example, the basic rational function would be 1 over x. And so we can see if we look at tables, obviously the domain of this one, hopefully obviously, is everything except 0, because that makes the denominator 0. And we cannot have the denominator be 0. And so our domain is negative infinity to 0, union 0 to infinity. So we're really just excluding that one point. And so what we're interested in, and what you need to be comfortable doing when we're looking at graphing these, is what happens around that point where the function does not exist. So it has to do something. And we'll kind of see basically what goes on as we look at a few of these examples. But what happens here? So you can see this side of the table, x is getting closer and closer to 0 from the negative side, or from the left side. So we say approaching 0, and then we put this little negative here. That doesn't necessarily mean that x is a negative number, although in this case it does. But really, more broadly, what that means is x is approaching 0 from the left side, which is negative in this case, but you could really have any number there. So what happens is x approaches 2 from the left side. So it doesn't mean negative necessarily, it just means the left side. And so in this case, you can see when x is negative 0.1, f of x is negative 10, negative 0.01, f of x is 100, negative 0.00001, and f of x is negative 100,000. So we can see that f of x is getting bigger and bigger and bigger on the negative side as x is approaching 0 on the left side. So we'd say that as x approaches 0 from the left, y is going to approach negative infinity, or y is going to grow in the negative direction without bound. And then we can see as we approach x from the right side, so we're kind of coming this way along the x-axis. So what is happening to the graph? And you can see from the table, you can see from the graph, as we get closer to the y-axis on the right side, the function is going up to positive infinity. It is growing without bound. So as we are approaching 0 from the right side, y is approaching positive infinity. And so what's going on here, you've probably seen this term before. This is called a vertical asymptote. So this is the line x equals 0. So x equals a number is always a vertical line. Y equals 0 is always a horizontal line. So in this case, we have a vertical asymptote at x equals 0. And we also have a horizontal asymptote at y equals 0. So you can see as we go out, and you can imagine this by plugging in bigger and bigger x values into the function, that y is going to get closer to 0. So they're actually going to get to 0. There's no way for this equation to equal 0. There's no solution to that equation. So the horizontal asymptote just means as x goes out to infinity, y is going to approach some value, whatever that horizontal asymptote is. And then with vertical asymptote, as x approaches some number, in this case 0, y is going to either go up to positive infinity or down to negative infinity, or could be both depending on the direction. So those are kind of the ideas of asymptotes. Asymptotes, generally speaking, you can think of as fences that when you are approaching a certain point, the fence will not be crossed. But we'll see a lot more of these as we go along and how they look. And so here we have definition. Let's zoom in a little bit. So the line x equals a is a vertical asymptote. So the vertical asymptotes are always x equals some number. And that's what happens when, if y is approaching positive or negative infinity, as x is approaching that number a from the right or the left, that's when we get a vertical asymptote. So this function will never actually touch that dotted line right there. It's going to get close to it, never actually touches it, and it's not going to move away from it. It's going to be at least that close, and then as it goes up, it's going to get closer and closer. And then we have a horizontal asymptote, is always written as y equals some number, and as x approaches positive or negative infinity, y is going to approach that number. So we can see two examples here. So we could have it to where it's coming up to the number like that, but we could also have functions where it crosses horizontal asymptote, but then it comes back down or goes back up, as the case may be. So it is possible to cross a horizontal asymptote, but at a certain point, it's not going to cross it again, and it's just going to get closer and closer. So this one, no matter how big x gets in the negative direction, the graph is not going to touch it again. It's just going to get closer and closer. Vertical asymptotes, on the other hand, cannot be crossed, because you can imagine if this is a vertical asymptote and you have the graph coming up like this and it crosses it, it can't come back, because then it's no longer passing the vertical line test. So vertical asymptotes cannot be crossed. Horizontal asymptotes can be crossed, but may not be. But after a certain point, the horizontal asymptote will not be crossed again. All right, so just a couple of notes on finding these asymptotes. So for the vertical asymptotes, all you need to do is set the denominator equal to 0 and solve for x. So these are all going to be all the zeros of this denominator here. And then for the horizontal, this one, it's a little bit more to remember, I guess, but it's actually these are easier to find. So n and m, you can look up here, these are referring to the degrees of these two polynomials. So if the numerator is less than the denominator as far as the degree goes, so like this is x cubed, this is x to the fifth, so that the degree on the bottom is bigger. So if we're in that case, then we have a horizontal asymptote at y equals 0. And so all that means is that y is going to get smaller and smaller as x gets bigger and bigger. Let's get down to this one. So now if it's the reversed, and we have, say, x to the sixth over x squared here. So the numerator degree is bigger than the denominator. In that case, we do not have a horizontal asymptote. Then the rational function is just going to get bigger and bigger, or go down to negative infinity. So it's just going to keep growing in one direction or the other. And then the third possibility is they could be equal. So we could have an x cubed polynomial up here. We could have an x cubed polynomial down here. So the degrees could be the same. And in that case, we just look at these two coefficients. So this is 2x cubed plus whatever else we might have. And then we have 3x cubed plus whatever else we might have. The horizontal asymptote would be y equals 2/3, because those are the two coefficients. And so that's all there is to it. So the horizontals are very easy, as long as you remember these three rules, and they're not too hard. And it makes, the more you kind of do, the more it kind of makes sense what's going on. And we may explain that as we go along. So we'll go ahead and stop this one, and we'll do some examples in the next one.